Hello friends, welcome back. In the previous video we learnt about diode circuit, its basics and open circuit test, and what are the conditions for on, conditions for off. And similarly we learnt how to find or on resistance, that is or on state resistance or on. So this topic is completed. I also solved some of the important previous year GATE and IES problems on the diode circuit basics. So now moving on to the application part. While coming to application part, we have here four applications. First is diode as a rectifier, half wave rectifier and full wave rectifier. Next clipper circuits, next clamper circuits. This thing is Zener diode, which we will use as a voltage regulator. So I am going to discuss this topic first. Diode as a half wave rectifier, diode as a full wave rectifier. In this we will have two configurations on full wave rectifier. One is center tapped configuration, one is full bridge configuration. So I will discuss the four topics in this video. So diode as a half wave rectifier. This is the circuit diagram of the half wave rectifier, guys. This is the step down transformer. Whenever we apply a AC input to the primary of transformer, it will step down that voltage. For suppose it is 230 RMS. It will step down to some 20 or 10 because diode cannot withstand that much high voltages. So after stepping down, only the magnitude change, waveform will not change. So the same waveform will be applied across the secondary of the transformer. Now we will analyze this circuit. First, when positive of the waveform is applied. So across the transformer, positive will appear here, negative will appear here. So if you assume this as an ideal diode, what is the first step? Open circuit the diode. If you open circuit the diode, here positive is connected, here negative is connected. So diode will be in on state. So during the positive half cycle, diode will be in on state. If diode is in on state, what is the voltage, output voltage? This is the on state representation of the ideal diode. So during the positive half cycle, output voltage follows the input voltage, V naught equal to Vi. Here I am showing this in waveform. This is during the positive half cycle. The output voltage is following the input voltage. Next we will see what will happen during negative voltage. See, I am applying negative voltage, so here minus will come, here plus will come. So the negative potential is connected to the P type of the diode and positive is connected to the N type of the diode. So diode will remain in off position. So during off position, it is the diode equivalent circuit, just open circuit it. So what will be output voltage? It will be 0. This I am showing here. This is during the negative half cycle. So what is basically a rectifier, guys? Rectifier is a device which will convert AC to DC. What is AC signal, guys? If an average over a cycle is 0, then it is called as AC signal. What is a DC signal, guys? If an average over a cycle is not equal to 0, then it is called as DC. So this is the basic rectifier action. This is a full wave rectifier because it is rectifying the total wave. This is a half wave rectifier which we discussed. So this is the basic rectifier. We have discussed the half wave rectifier. So guys, you should learn the formulas regarding these two waveforms. This not only helps in analog electronics but also in networks and also in power electronics. So you should be aware of this two waveform. First one is this waveform. So for this waveform, V average will be 2 Vm by pi, where Vm is the maximum voltage and Vrms will be Vm by root 2. For this kind of half wave rectified waveform, V average will be, hence here it is 2 Vm by pi, here it will be Vm by pi, and Vrms is Vm by 2. I can derive this guys, but it will kill our time, that is not required. So just remember these two formulae. For this kind of waveform, V average is 2 Vm by pi. For this kind of waveform, V average is Vm by pi. And next, if you want to analyze the quality of this waveform, we will analyze by using the ripple factor. For DC, we will use ripple factor. For AC waveform, we will use total harmonic distortion. So we are not talking about AC now, we are talking about DC. So we will use the ripple factor to analyze the quality of this waveform. So what will be the original DC waveform? This is the original DC waveform. But we have a waveform like this. So to analyze the quality of this waveform, we will use ripple factor. What is the formula of ripple factor? Root over form factor square minus 1. And form factor is Vrms by V average. So now we are talking about the second waveform, because this is the waveform we got here, half wave rectified output. So we will find ripple factor for this waveform. For finding ripple factor, we should find form factor first. So what is form factor? Vrms by V average. Vrms is Vm by root 2. Sorry, Vrms is Vm by 2. V average is Vm by pi. So form factor is pi by 2. Next. Similarly, ripple factor. Root over pi by 2 whole square minus 1. So I got 1.21. This is the ripple factor, guys. So with this, our half wave rectifier is completed. I am summarizing it. During the positive half cycle, diode will be in on condition. So V0 is equal to Vi. During the negative half cycle, diode will be in off condition. So V0 is equal to 0. So this is our output. According to this output, we analyze the output average, RMS and form factor according to the ripple factor. We got ripple factor is equal to 1.21. So this is our half wave rectifier. Next, moving to full wave rectifier. In diode as a full wave rectifier, we have two configuration, guys. One is center tapped configuration, another one is full bridge configuration. Coming to center tapped configuration, we will center tap the secondary transformer. So I will explain you how will this center tap work. Suppose this is a 1:2 transformer. Assume I am applying primary voltage like this. While coming to secondary, let this be my center tap. Let the peak voltage be 10 volt. Since it is 1:2 transformer, I will get 10 here and 10 here. Total 20. It should convert to total 20 like this, because it is 1:2 transformer. So this is divided into 10 here and 10 here. I am taking the notations as plus minus plus minus. For this I am taking this as difference. For this I am taking this as difference. So this waveform is divided into like this one and this one. So we will analyze the center tapped configuration by using this explanation. So during positive half cycle, what will happen? Plus will induce here, minus will induce here, because this is the waveform. And while coming to here, plus will induce here, minus will induce here, because this is the waveform in the positive half cycle. And while coming to negative half cycle, just reverse. Friends, that is nothing but two half-wave rectifiers connected. We have already seen half-wave rectifier, it will be having only this component. Here we are connecting the two half-wave rectifiers, that is the center tapped configuration, and we are connecting the load between this center tap and this point. So during positive cycle, what is the voltage here? Positive. What is the voltage here? Negative. Similarly, what is the voltage here? Positive. What is the voltage here? Negative. So if you observe this diode will be in on state, and negative is connected to the P type of diode too. So this diode will be in off state. So now this is our circuit. So what will be V naught equal to? Just Vi. Next, during negative cycle, what are the polarities guys here? Here it is minus, here it is plus. Similarly, here it is minus, here it is plus. See, minus is connected to the P type, so this will be in off state. Here positive is connected to the P type, so this will be in on state. If this is in on state, see, this is the circuit which is operating. Again the correct direction is in this, current is in the same direction. See, in the positive half cycle, we got a circuit like this. Current is flowing like this. In the negative half cycle, we got a circuit like this. Again the current is flowing in the same direction with respect to the load. See, if this is the load, current is flowing like this. If this is the load, current is flowing in the same direction. So here load voltage is not changing. Here also V not equal to Vi. So again it comes in the positive half cycle. Why? See here, see the current direction. During positive half cycle, current is flowing in this direction. During negative half cycle also, current is flowing in the same direction. So our load voltage will not change. It is again coming in the positive side. So this is the operation of the central tapped transformer. While coming to full bridge configuration, during the positive half cycle, here positive is applied, here negative is applied. So diode D1 is turned on and diode D3 is turned on. So our circuit will be like this. This is the output voltage. So output voltage equal to input voltage during positive half cycle. So I'm writing this. Next, during negative half cycle, minus is applied here, plus is applied here. So this will be in D4 is in forward bias and D2 is also in forward bias. So our circuit will be like this. Here also again V0 is equal to Vi. See, because we are applying a negative voltage, but here V0 is taking the negative of it. So this will again become positive. So I am again drawing in the positive cycle. So this is the operation of center tapped configuration. This is the operation of full bridge configuration. Now we will analyze the ripple factor. So before going to the ripple factor guys, why are we having two configuration? Only one is enough, no? So why? Because if you see the voltage rating of the diode here, it will be 2 times of the supply voltage. Here it will be equal to supply voltage. And in center tapped configuration, you require a center tapped configuration also. That is center tapped transformer also, which is very costly and we require accurately. That is impossible. And here diode is having rating of 2 times the supply voltage. But here no center tap is required and diode is having the rating of supply voltage only. So it is more costly. It is less costlier. So full bridge configuration is preferred. We don't prefer the center tapped configuration. So result of both configurations is same. a full wave rectified output. Next we'll analyze the ripple factor. So this is the output waveform of full wave rectifier. This is the maximum voltage Vm. So RMS voltage will be Vm by root 2, average voltage will be 2 Vm by pi. I taught this thing just 5 minutes back. So we should find the ripple factor. For finding ripple factor, what is the formula? Form factor square minus 1. What is form factor? Vrms by V average. So Vrms is Vm by root 2 and V average is 2 Vm by pi. So pi by 2 root 2 is the form factor. So what is ripple factor? Root over pi by 2 root 2 whole square minus 1. I am getting this as 0.483. See, if you observe half wave rectifier, we got ripple factor as 1.21. In full wave rectifier, ripple factor is 0.483. For ideal DC, ripple factor should be 0. So now tell me friends, which is best, either half wave or full wave? Obviously full wave is best because we are getting less ripple factor. It's only 48.3%. So we should remove this also by using filters that we will discuss at last. So this is the analysis of full wave rectifier, guys. Now I will solve some previous year gate question based on these rectifiers. This is the first question, guys. Input voltage is pi sin omega t. There are 3 diodes. He is asking the DC component of V1 and V2. DC component is nothing but average. He is asking V1 average and V2 average. So let me solve this first. This is our input voltage. Maximum is pi. Let me draw voltage for V1. See, during positive half cycle, open circuit all the diodes. During positive half cycle, D1 will be in forward bias because positive is connected to positive. And D2 and D3 will be in reverse bias. See here. This is the circuit. So only this will be in forward bias. This is connected to positive. This is also connected to positive. So these two will be in reverse bias. This thing will be in forward bias. So if diode D1 is in forward bias, this is our circuit. See, it is V1 resistor or this is V2 resistor or. During positive half cycle, this is our equivalent circuit. So this voltage is divided equally among V1 and V2. So let this be V1. Let it be V2. So during positive half cycle, it is divided equally. So you will get pi by 2 here and pi by 2 here. During negative cycle, what will happen? Negative is connected here. So diode D1 will be in reverse bias, off state. Diode D2 is forward biased and diode D3 is also forward biased. See the equivalent circuit here. See, here minus is connected to P. So this will be in reverse bias. Here minus is connected to N. So this will also be in forward bias. This will be in forward bias because minus is connected to N type. And if you observe here, this P type is connected to this positive terminal. So this diode will also be in on state. So this is on state. This is also in on state. This will be in off state. So if I draw the equivalent circuit, it will be like this. Since this diode is short circuited, our output voltage V2 will be 0. So entire voltage will appear across V1. This is minus plus, but here V1, it is stating the negative of the voltage. So it will again become positive. So this will be like this now. This magnitude is pi because total voltage appear. In the positive half cycle only half voltage appeared and V2 is 0. So this is our waveform now. He is asking us to find the average value of V1 and average value of V2. If it is having two different peaks, let it be Vm1 and Vm2. Then average value will be Vm1 by pi plus Vm2 by pi. If Vm1 equal to Vm2, then average value will be 2Vm by pi for full wave rectified waveform. So what is the average value here? Pi by 2 by pi plus pi by pi. So answer is 1 by 2 plus 1, that is 3 by 2. While coming here, average value is what? Only Vm by pi because it is a half wave rectified waveform. So that is pi by 2 by pi. Answer is 1 by 2 volt. So moving to next question. So this is the second question, guys. If you observe here, during positive cycle, D1 will be in on condition. During negative cycle, D2 will be in on condition. Why? If you draw the equivalent circuit of this, so during positive, P is connected to plus, N is connected to minus. So this will be in turn on. While coming to here, N is connected to plus. So this will be in off region. While coming to negative, P is connected to minus here. So this will be in off region. Here N is connected to minus. So this will be in on region. So during on positive, this will be in on. During negative, this will be in on state. So if you observe here, guys, during positive cycle, I have drawn the equivalent circuit by turning on this diode D1. So this is the equivalent circuit. So how to find this V0, guys? Just we'll apply voltage division rule. Here voltage is Vi between these two terminals. So what is the voltage across V0? Sorry, voltage across 5 kilo ohm resistor. Vi into 5 kilo by 5 kilo plus 10 kilo. It is just appearing like this, guys. 5 kilo, 10 kilo, Vi. We need this voltage. So V0 equal to Vi into 5 kilo by 5 kilo plus 10 kilo, which is V0 equal to Vi by 3 during positive cycle. While coming to negative cycle, so this diode D2 will be in on state. So this is the equivalent circuit. What will be V0? Vi into 5 kilo by 5 kilo plus 5 kilo. So the direction of current. During on state, the current will flow like this. So V0 will remain in the same direction. And during negative cycle, current again will flow like this through this diode. So V0 will again retain the direction. So V0 equal to Vi into 5K by 5K, that is equal to Vi by 2. So now this is our answer. During positive half cycle, V0 equal to Vi by 3, and during negative half cycle, V0 equal to Vi by 2. That is, this maximum voltage will be 6 pi by 2. This by 3. This maximum voltage will be 6 pi by 2. So what is the answer? 6 pi by 3 by pi plus 6 pi by 2 by pi. 2 plus 3, that is 5 volt. So this is the end of the video, guys. I have explained the concept. I have solved some previous year problems, and in the next video I will explain about the clipper circuit. If you like my explanation and if you are learning something out of it, then do subscribe to my channel and like my Facebook page. I provided the link in the description. Thank you.